Kia ora, Year 12 and 13. In this video I'm going to work through the proof of the standard form of an ellipse equation. So this is out of the appendix to Delta, and I'm going to follow the notation used there, but you can find this on the internet in lots of different places. So the algebra in here is a little bit messy, but I think it's worth going through so that you understand where the equation came from. So first of all, what is that equation? Well, it's x squared over a squared plus y squared over b squared equals 1. And that gives us this shape of ellipse. So it's a horizontally stretched one, and we've got intercepts at negative a and a, negative b and b. The unseen thing in here, but really important, are the two foci, and we're going to put those at negative c and c. Now, the definition of an ellipse is the locus of points such that when I take a point and impose the condition that the distance of that point from each of the foci added together is constant, I get an ellipse. So I'm going to try and say that again. If this is point P and this is F2, we'll call this F2 and F1, if we look at the points that satisfy this condition, so that the distance from F1 to P plus the distance from F2 to P is always the same number, then it traces out an ellipse. And when we do this in class, we'll do this with a big piece of string at the whiteboard. Okay, and we'll also have a look in GeoGebra. But today I want to look at the proof of where the form of the equation comes from. So just before we start, I'm going to not have the ellipse there. I'm going to go back to just having the point and the two foci. So I'm going to do that on a new slide. Okay, so here are my normal axes. We're going to put the first focus on here, so it's at negative c0. Right, and the other one here. Okay, and here's my point here. So, if I want xy to be on the ellipse, the condition is that the distance here plus the distance here is equal to some constant. So let's have a look at what those two distances are. So that's just an application of Pythagoras. So this one first. Okay, so we're going to have, by Pythagoras, x minus c squared plus y minus 0, so plus y squared, plus the second one will be x plus c squared plus y squared. And that's equal to some constant. Now it turns out the algebra is tidier if instead of calling this k, we call it 2 times a. Right, so we're going to rename k as 2a. So the first thing we can do here is we've got square roots on both sides, so that's not so nice. We are going to start out by just having one square root on this side. So I'm going to leave the second of the two on the left hand side, and I'll write equals 2a minus this. Right, so I've still got lots of yucky square roots. What can I do? Well, I can square both sides. So I'm going to do that next. Okay, when I square, so on the left hand side, I'll just write it out again here, x squared plus y squared. It's the left hand side. Here I've got 2a minus x minus c squared plus y squared. So squaring both sides, well, on this side I get x plus c squared plus y squared. Okay, and on this side, well, I have to think about what happens when I square this. So this is expanding a square. So this term here squared gives me 4a squared minus, right, so 2 times this one, right, so minus 2 times 2a times the square root of that thing there, like that, plus, now this thing squared is going to be nicer, I'm going to get rid of my square root. So it will be x minus c squared plus y squared. So we can see we're going to be able to knock some things out of both sides already. So my y squared here is balanced with my y squared here. So let's do a little bit of expanding on what's left. I have x squared plus 2cx plus c squared is equal to 4a squared minus this hideous thing here, which I'm still not loving. Here we go. Right, so there's that. Now I expand out that next bit and I get x squared minus 2cx plus c squared. So again I can do some knocking out. The x squareds knock out and so do the c squareds. So that's a little bit better. Okay, so time for a little bit of cleaning up. We've got 2cx is equal to 4a squared minus 2cx here minus the icky thing with the square root there. So I can collect up like terms, so plonk that over to the side and I get 4cx equals 4a squared minus 4a times this here. Now I've got a nice common factor of 4, so this is why having it defined as 2a was all good. So we'll knock out the 4's, divide everything through by 4. So we've got cx is equal to a squared minus a times that. Now I'm going to rewrite that. So I have a times bracket, so I'm just rearranging because I want to just get the square root thing on the left hand side. And now here I've got a squared minus cx. So it's starting to look a bit better because if I square both sides, I'm going to get rid of my square root last. So let's do that now. So squaring both sides, I'll just put a note there of squaring, a squared times x minus c squared plus y squared. So that's that squared, and the square root squared gets rid of the square root. And over here, I'm going to square this. So here we'll have a squared times x squared minus 2cx plus c squared plus y squared. And that equals a to the power of 4 minus 2a squared cx. Right, so 2 times this plus c squared x squared. Right, so let's expand out the left-hand side and then we can knock some things out. A squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared equals a to the 4 minus 2ac squared x plus c squared x squared. So let's see what can vanish in there. Well, I've got this minus 2ac squared x and this here. And sadly that's about all that goes. So next slide, but we're getting somewhere now. Okay, so a squared x squared minus c squared x squared, bringing that over, plus a squared c squared plus a squared y squared equals a to the power of 4. So that's getting everything to one side except for the a to the 4. Now we're going to look at our x squared. Let's factorise what we've got with x squared. A squared minus c squared plus a squared y squared is equal to a to the 4 minus a squared c squared. So that equals a squared times a squared minus c squared. So believe it or not, we're nearly there. Think about where we're going. We want to get to x squared over a squared plus y squared over b squared equals 1. Now obviously there's no b squareds anywhere, so that's going to be something that we define very near the end. But for now, the first thing we might do is divide both sides through by a squared minus c squared. So that's going to give me x squared plus y squared times a squared over a squared minus c squared, and that equals a squared. I want to end up with a 1. So now I'm going to divide through by a squared. And I'll get x squared over a squared plus y squared over a squared minus c squared equals 1. Okay, and now we're going to write let b squared equals a squared minus c squared. And we are finished. Okay, so quite a lot of work to do that, but I wanted to show that to you because it's a great example of how we can start with something very, very simple, so the idea of two distances added together, and follow through a long chain of reasoning and pop out the other end with a really simple formula for the equation of an ellipse. So thanks for sticking with it to the end. If you really want to get on top of this, you probably need to go back and follow it through step by step yourselves.